All right, so last Thursday, we started looking at signal splitting in NMR, specifically proton NMR. You normally don't see signal splitting in carbon NMR unless you're doing an advanced experiment. And we said if you have one 3-bond neighbor, you get split into a doublet. So in this case, HA has one HB neighbor, so it gets split into a doublet. Middle example, we've got two 3-bond neighbors, so it gets split into a triplet. If we have three 3-bond neighbors, get split into a quartet. And I told you some general guidelines for determining signal splitting, right? So use the n+1 rule. So pick one of the protons in your unique set and then ask yourself how many neighbors are there to that given proton. And then we said that you can only feel protons that are 2 or 3 bonds away. You don't count 4-bond neighbors. They're simply too far away. And then we said that HAs can't be split by other HAs, meaning equivalent protons can't split one another. And then HAs cannot find neighbors if you have to go through a non-carbon atom. All right, what we're going to talk about today is getting into some fine detail. So if you notice, in this doublet here, we've got two peaks that are spaced apart. That's called a coupling constant, and there's actually a lot of fancy physics that's going into that, but we're going to boil it down to the most essential part. So let's talk about how far apart those peaks get spread. So like I said, a coupling constant is the distance between peaks. And this is going to be in hertz. That's how it's usually measured. It's not normally measured in ppm because ppm can vary a little bit. All right, so it's going to be in hertz, and it's only applicable for split peaks, right? So if you're a singlet, you're obviously not going to have any gap between peaks. So let's take a look at an example here. So I'm going to take a look at one of the aldehyde peaks in our compound, and I'm just going to make up a new molecule, actually. So I'm just going to say that that's coming off of something else. We've got two protons. We've got two protons here. I've got proton HA, and then over here I've got proton HB, right? All right, so if we think about HA, if it's unsplit, we can assume might have some sort of signal. And in this case, I don't know if you can see my graph paper on here, but I'm measuring it as 4 units tall. So this is HA unsplit. Sorry, I just got a new laptop to replace my glitchy one, and I don't know if it's really improving the situation. Let me try this. Making a lot of noises. All right, so let's try this again. So this is HA as an unsplit signal. And if we think about HA, it's got two 3-bond neighbors, right? It's got HB on the left and HB kind of further away on the right. So it's got two neighbors. And so what we're going to do is one of these neighbors is going to get split HA once, and then the second HB is going to split it again. So let's think about this, right? If we split this, it's going to be half as tall, right? So this is HA split by 1 HB. So we're not counting the second HB at this point, but does it make sense that the signal's half as intense now? So basically this distance between these two new peaks can be referred to as a coupling constant, and we often abbreviate that as J. And then with this J symbol, we want to indicate what protons we're referring to. So in this case, it's the split between A and B. So we'll call this JAB to indicate that's how far the signal is being split. All right, the next HB, though, should split it the same intensity, right? So let's go ahead and do that. So if we split it the same intensity, let me clean this up a bit. It's going to be split like this, and like this, right? So that leftmost peak is now going to be half as tall, and it's going to be split like that, right? And then we can do the same thing for this peak over on the right-hand side now. This peak will also be split by the second HB. And so we can show this being split again, and now this middle peak is going to actually be twice as tall. So if we look at this, right, it makes sense when we look at the ratio of this peak splitting. This peak right above here is going to be a relative size of 1 to 2 to 1. And this splitting is going to occur a second time down here. This is going to be JAB. So it's splitting each of those peaks that were split once one more time. So let's make a note of this down here. So this is going to be HA split by second HB. Yeah?
So it's split a second time because we have two HBs?
Exactly. So it's split twice because we have two HBs. Oh my goodness. Sorry. Let me close this and restart it. All right, so this is HA split by that second HB. Okay, so this kind of explains in an abstract way why we observe a triplet is when we split the peak the second time, the two peaks overlap, right? And that makes them twice as tall, so it's a 1 to 2 to 1 ratio. And so this gives you that signal shape that looks a lot like a triplet. Or be something like this. So if we zoom in really, really far on the triplet, we can actually measure the distance from one of the peaks to another, and we would call that JAB, and we would actually report this out whenever we publish NMR data in literature. So this would be a zoom in of a triplet. All right, so now let's take some different examples. We'll try to work on them. All right, so in this example, we're actually going to switch to an alkene. And I'm going to put a fluorine here, a chlorine here, and a second proton here. All right, how many unique protons are in this compound? 2, right? This doesn't have symmetry in it. So I would call the proton on the left here HA, and I would call this one HB. We know that they're different from one another. All right, so if we think about HA, what will it be split as? It'll be split as a doublet. So HA will be a doublet. And we know that its 3-bond neighbor is HB, so we're going to assume that HB is the thing splitting it into the doublet. All right, and then over here, what about HB? It's also going to be a doublet. They're going to be 2 distinct doublets. They're not going to share the same frequency on the NMR spectrum. And this one's going to be split by HA. All right, now this may seem kind of intuitive, but let's say we've got HA and it's a doublet that looks like this. Actually, let me clean this up a little. Yeah. So this is my HA doublet. And then maybe somewhere else in the spectrum we have our HB doublet. That looks like that. So this would be the HB, sorry, doublet. We can actually measure the distance between these peaks. And so, for example, we could call this JAB, and then over here, we could call this JBA, right? And what this really means is that they're splitting each other with equal intensity, right? So in this example, HA splits HB at the same intensity. Meaning JAB is going to be equal to JBC. Sorry, I saw hands pop up somewhere. Yep. Oh, JBA. Sorry about that. So it's basically just saying that they're going to have the same relative splitting pattern. So if you are trying to find neighboring sets of protons in some sort of unknown spectrum, you can actually measure the coupling constant. And if you have another peak somewhere else in the spectrum with that same coupling constant, that's a big clue that they're neighboring proton sets, right? So you can actually help use this to help piece together the identity of some sort of unknown compound if you're given NMR data. So it's kind of clever. There's also other techniques you can use besides just looking at the coupling constants. All right, now I'm going to blow your mind with the weird example. All right, so in this example, we're also going to stick with an alkene. Whoa. And how many different sets of protons are in this alkene? What's that? 3, right? So we've got HA over here, and then I'll call this HB, and then I'll call this one HC, right? What I want to do is just to focus in on HA right now. So let's just focus on HA. We're going to ignore the other one just right now. Intuitively, when you look at HA, what should you infer that it would be split as? How many 3-bond neighbors does it have? 2. So we would naturally assume this should be a triplet. The reality is the physics aren't that easy, right? In this case, if HC and HB were equivalent, then yes, it would be a triplet. But they are radically different from one another. Why is that? One's cis, one's trans, one's also way closer to an electronegative atom. So they behave completely different from one another, meaning they split HA to a different intensity. So now let's take a look at this, kind of same idea, and we'll do HA unsplit up here. What we're going to do is we're going to split it by HC first. So HC, by its very nature, is going to split it to a much higher degree, meaning spread out that split much farther apart. So we can go ahead and do that. And just like before, it's going to be half as intense. So now we can make a little note down here that this is going to be HA that is split only by HC.
Does it matter whether you start with HC or HB in this case?
Not really. However, most people will start with the one that has the largest coupling constant just because it's easier to draw that first rather than have your smaller one and have to branch out from that. Okay, so we've got HA split by HC, but we know that there's also HB. In this case, we already identified this part as the coupling constant. We'll call this JAC. So So it's proton A being split by proton C. However, we should have JAB, but that JAB distance is going to be different than JAC. Okay, so now let's go ahead and do that one. And this one's going to be a bit different. The proton B is going to split it to a much lower degree than proton C. Okay, so when we go ahead and we measure this, we're going to have some sort of signal that's this far apart, and we're going to split this peak in half. And it's going to be basically 1 unit tall, 1 unit tall, 1 unit tall, 1 unit tall. And each of these is going to be split to the same degree, and we'll call this JAB. And we'll make a note down here that this is HA further split by HB. Okay, so the weird thing is when we zoom in on what we would have thought would be a triplet, the peak looks a little bit different. Instead, let me actually zoom in a bit more here. It's going to look like this, spread out like this. Does anybody know what they're going to call this? Voodoo? It's actually way more fun than that. It's called a doublet of doublets. Oops. And this is just abbreviated as DD if you ever see it in an NMR spectrum. And really this occurs when your coupling constant for one neighboring proton is way different from another neighboring proton. So they actually cause this complicated splitting pattern. Yep?
Just for some weird examples, right now, to say we had an impurity while we were doing this and we had a carbocation, how would that form a charge interact with this?
So that's a good question. Carbocations are so unstable you really can't see them by NMR with rare exception. Impurities will do their own unique thing, so we're going to kind of assume pure compounds. This is a really nice, clean example. You often see doublets of doublets or things like that with alkenes. However, oftentimes they get pretty complicated. So there's situations, for example, where you might have a doublet of quartets. And so if you have a doublet of quartets, you've got 4 peaks like this, like your fingers, right? But maybe they're not split apart very far. Maybe they're overlapping doublet of quartets. Do you know what we call an overlapping doublet of quartets? You're close. So you said pane. We call it a multiplet. Just because it's so hard to interpret when you have 2 overlapping complicated sets of signals, people are like, you know what? It's a multiplet. We're not even going to try bothering deciphering what that is. It's too complicated to decipher. Doublet of doublets you might occasionally see because they're common with alkenes, which is why I like to show you these. There's a lot of weird examples like this. This is kind of as far as I want you to know in case you run into some of these weird situations. Make sense? All right, so we're going to kind of stop there, and then we're going to start looking at where peaks show up in NMR. Yeah?
So if we have neighboring hydrogens that are different, like HC and B, will we always see a doublet of whatever?
Yeah, so that's a good question. So if you have 2 different types of neighboring protons, will you always observe this complicated splitting? Not always. It depends on the nature of those neighbors. Sometimes the coupling constants are so similar that they're almost identical, and so it follows the normal n+1 rule, right? So take alkanes, for example. For most alkanes, we don't observe the weird splitting pattern because one sp3 hybridized proton is going to be very similar to another sp3 hybridized proton. However, in this example, we had cis and trans. That's what really caused it to be different. Yeah, good question. All right, so now let's try to take a look at where peaks show up in NMR spectra. And this is called chemical shift or resonant frequency, meaning are they really far to the left on the spectrum or really far on the right. So let's take a look at chemical shift. All right, and that's typically done with this delta symbol. And this is kind of been standardized lately as ppm. So that's parts per million. It's not actually a concentration unit. I'm honestly not super sure why they chose parts per million, but it's technically a frequency. But what it is it's the observed shift from TMS, and I'll describe what a shift is. And I'll also describe what TMS is in hertz times 10 to the 6. And then your numerator is going to be your operating frequency. So every NMR operates at a different frequency. So for example, the NMR that we have upstairs that we'll be using in lab is a 60 megahertz NMR. So you do need to multiply 60 times 10 to the 6 because it's megahertz, not just hertz, right? If you go to a fancy school, oftentimes they have cryo-cooled supermagnets that go all the way up to 600, 800, even a gigahertz. The higher the operating frequency, the more sensitive the instrument in general. So ours is 60 megahertz. That's kind of like a baby NMR, but it's nice because we don't need to cryo-cool it. It's easy to use. All right. So what the shift means is the distance that the peak is from some sort of reference signal. Was that what you were going to ask?
No, I was actually going to ask if they're all like absolute zero or close to absolute zero inside.
Inside the magnet? Close. So the big superconducting magnets are cooled with liquid helium. So they're, I think, 5 degrees Kelvin.
Yes, it's
Very, very cold, but they're very expensive to run. Liquid helium's not cheap. So typically you have to be doing a lot of research to justify the cost of having that equipment. Yeah, so the numerator here is basically saying the peak that we're looking at is how far away from the TMS standard in hertz. And TMS is tetramethyl silane. It's an NMR standard. Basically, people will add this into their NMR samples to tell you where 0 is. Otherwise, it's really hard to know what you're looking at. So they'll just say, we'll pop in a little bit of this. We know it will always show up at 0, and then we'll tell the instrument to adjust from there. So it's just an internal standard that's used. Yep.
Is there a reason why that shows up at 0 that we know, or it just does?
So it was basically just arbitrarily picked to be a standard because it's very reliably at one frequency. It doesn't move around. And it was very close to what was previously designated as 0. So they just chose that. Yeah. All right, so let's take a look at the NMR scale. All right, and with this NMR scale, typically it's about 0 to 12. Sometimes you see it even wider than that. But it goes from 0 on the right to larger numbers on the left, and the scale is always in ppm. And TMS, like we said, is the reference, meaning the thing we'll often add to our sample, so we know where 0 should be, and we can actually shift the scale to adjust if it's a little bit off. But in general, for the NMRs that we'll look at, the peaks will fall in this 0 to 12 region. If you do really crazy NMR, sometimes you can actually get negative ppm, or you get signals going all the way up to the 20s or 30s, but that's super oddball examples that we'll just never see. All right, so now the question is, will our peak show up closer to 0 or closer to 12, and how can we predict that? And there's two main things that will affect this. So two main factors affect chemical shift. And these are actually fairly easy to remember. So the first one is electronegativity or induction. Which one do you think has a larger effect? Electronegativity. So it does drop off, but induction you might see some small effects. So in general, if we think about our 0 to 12 scale here, and we'll do this in ppm. I'm going to actually split this up. We'll do 10 and 5. Electronegative elements will shift compounds closer to 4 or 5-ish. I should actually do it more about this. So if a proton that you're looking at is really close to an electronegative atom, or even bonded to oxygen or something like that, quite often it'll show up closer to 4. Less polar things will show up way closer to 0. So that's one useful trick you can use, is more polar things get shifted to a higher ppm. The other one is aromaticity. Okay, so aromaticity, if you think about it, is usually described in reference to benzene. So benzene is a classic aromatic molecule. However, let's think about benzene on its side. So I'm going to show this as kind of dashes and wedges. Each one of the carbons in benzene is sp2 hybridized, so we've got these p orbitals kind of sticking up and down. And we've got electrons that are actually delocalized across both lobes of that p orbital, so it's almost like a big cloud of electrons above and below. So it's kind of hard to draw. But you can imagine it, right? All of those p orbitals are aligned, meaning those electrons can delocalize. And we know this because of resonance, right? So this electron can move, or those electrons can move there, those can move there, those can move there. We can delocalize electrons all the way around the ring. All right? The weird thing is, when electrons do that in a ring system, you essentially are creating current. And when you have current, you make a magnetic field. So you're creating a magnetic field within a magnetic field. The big thing I want you to remember somebody's hicking up because they're so nervous about this. I don't know if hicking up is the right verb for that, though. All right. Anyways, aromatic protons normally show up around 7 to 10 ppm. Yep.
So would that mean that any molecule with any chance at resonance would also shift from what?
No, it's unique to ring systems. So you have to have a ring current going on. If you just have resonance, that's not a current necessarily, where a ring system is a current. This is called the anisotropic effect. All right, so those are the two main features. However, I have good news. If you noticed on the cheat sheet that I gave you on the last exam, I also gave you approximate chemical shifts for various functional groups. So beyond that, you're given a cheat sheet to use on exams and quizzes. So for example, right here, it says that protons coming off of carboxylic acids typically show up around 10 to 12 ppm. So you can use that as a really good guide. If you think about protons coming off of aldehydes, they're normally about 9 to 10. And then if you notice this right here, that's the aromatic protons. That's due to that mini magnetic field caused by aromatic ring systems. So that's going to shift it. In this case, they're showing it 6 to 9. Sometimes you see 7 to 10. It's going to be in that approximate ballpark. If we think about alkenes, meaning protons coming off of alkenes, they normally show up around 4 to 6 ppm. And then over here, I'm going to highlight it. We've got alcohols, meaning protons that are attached to alcohols will show up anywhere from 0 all the way up to 5. It really depends on solvents. In addition, if you have protons that can hydrogen bond and you're running your NMR in a solvent that can hydrogen bond, sometimes those peaks will broaden out just like with IR. And sometimes they'll broaden out so much you just can't even see them anymore, meaning they're exchanged away. Because if you do hydrogen bonding, you can actually break and exchange your proton with a proton from your solvent. And our solvent always has deuterated atoms on it. So it might slowly disappear. Those are called exchangeable protons. All right, going further, you can see terminal alkynes will show up about 2 to 3. If you have protons coming off of ketones, typically, again, about 2 to 3. If you have a CH3 group coming off of an aromatic ring, that's also about 2 to 3. And then primary, secondary, and tertiary protons typically show up below 2. The weird example, like I said, is if you have this atom X that's electronegative, that's the inductive effect kicking in, and that might shift it, instead of being from 0 to 2, between 2 and 4. So you can use this as a rough guide.
So then how do you determine between like the 2 to 4 of the XCH as opposed to the COH?
That's a good question. So if you're looking at an unknown spectrum, you've got a lot of clues beyond just chemical shift, right? You can look at integration. You can look at signal splitting. This is just one clue we have when we're working through solving these. But it's a good tool to have. All right, and then down below, I wanted to show you this really quick. This is the approximate frequency for carbon NMR, which we haven't really talked about yet. And we'll jump into that next. But if you notice, the scale from carbon 13 NMR goes from about 0 to 240 parts per million. This is a completely separate experiment. You'll get a completely separate spectrum. But same idea, it classifies the different types of carbons and tells you approximately where they should show up. So this will be given to you on exams and quizzes. I do not expect you to memorize this. Yep.
Is there a reason why it goes from bigger to smaller?
It has to do with the nature of the nucleus that you're looking at. In fact, I remember in grad school, I did platinum NMR, completely different scale. In fact, I don't even remember what the scale was. Same thing if you do nitrogen 15 NMR, completely different scale. Same thing with fluorine NMR. If you do fluorine NMR, it's wildly different. It just depends on the nature of the nuclei. Yep. All right, so let's jump back into carbon NMR. Good news is carbon NMR is way easier. First thing to remember with carbon NMR is it is less sensitive. Does anybody know why carbon 13 NMR is less sensitive? It's what? So carbon 13 doesn't really decay, not at an appreciable rate. Carbon 14 eventually does. Think about mass spec. What's the most abundant form of carbon? Carbon 12. We can't look at carbon 12. Why is that? Has an even mass number. We can look at carbon 13 because it has an odd mass number, but what's the problem with carbon 13? It's not abundant. It's only 1.1% abundant in nature. Which means a few things. If this experiment is less sensitive, what you have to do is maybe instead of running one scan, you have to run 100 scans. Meaning take 100 different spectra and then average them out. That way you can subtract out the noise as much as possible. In fact, our NMR that we have upstairs, you would probably have to run your carbon NMR overnight to get a decent spectrum. It takes much, much longer to acquire a carbon 13 spectrum. All right, next thing is there's usually no splitting. unless you're doing a special experiment with carbon NMR, they all show up as singlets. So you don't observe doublets, triplets, and so on. So you don't need to worry about splitting at all. Next one is there's usually no integration. There are special experiments you can do, but to be honest, those special experiments take so long, people normally don't bother doing them. All right, so you can't really get a good feel for the number of carbons making up a specific signal. However, you do get an idea of the number of unique carbons in your compound. All right, and then like I said, you can use that cheat sheet to help narrow down what sort of functional group that carbon likely is a part of, right? So that cheat sheet should be your best friend over the next few days. You want to have that by your side when you're working through a lot of these problems. All right, the weird thing you might see occasionally, like we said, the scale goes from 0 to 240 ppm, is you might see this weird little peak. It's 3 equal peaks, so it looks kind of like a triplet. This is our solvent peak, which is usually deuterated chloroform, so CdCl3. And this normally shows up at 77 ppm. And in fact, we use this solvent peak as an internal standard, so we tell the NMR that peak should be at 77, shift things around so that it fits right. So if you do see those 3 peaks, they don't belong to your molecule, it's just the NMR solvent. The unfortunate thing with carbon NMR is we can't really avoid having C13 in our chloroform. We can't isotopically get rid of it. So you're always going to see that solvent signal. Does anybody know why we use CdCl3 instead of just regular chloroform, meaning CHCl3? Well, that and the H would show up, right? So if we ran our solvent or our NMR in a solvent that had protons rather than deuterium atoms, all we would see is our giant peak for our solvent, and we would obscure any of our normal signal for our compound that we're trying to dissolve, right? So that's why we tend to use deuterated solvents for NMR spectroscopy. Does that make sense? All right, so what we're going to do tomorrow is we're going to spend the entire day just going through practice problems. I gave you a big stapled set of problems. You have the molecular formula, so you've got a few clues to get started. One thing I really like doing is solve the HDI. So the HDI can be a valuable clue. Then you can look at the number of signals that you have, the signal splitting, and then where they show up, meaning what ppm they show up as, and then try to deduce what the structure of each of those compounds is. But we'll practice tomorrow if you're struggling.